The lecture is organized by the Knowledge Engineering and Semantic Web Conference and the Prague Computer Science Seminar. And it's my pleasure to give the microphone to Wojciech Svátek, who will chair this lecture and guide us through this interesting talk. Thanks.
Welcome everybody, both people who came just for the Prague Computer Science Seminar and people who are here for the KESW conference. First, as regards the PIS seminar, this is the 22nd seminar already, and it's actually the third seminar, if I remember well, by a foreign speaker who doesn't have Czech roots, or at least as far as I know. It's the first speaker, I would say, who is engaged in the field of semantic web and knowledge engineering. So I'm very happy to have a speaker of this kind. And it's definitely not just one of a large crowd. It's one of the most important persons in this field. It's no longer there, but you could see a long list of committee chairing and achievements and awards. I could also add that Steffen's H-index in Google Scholar is about 80 and over 26,000 citations, which really makes him one of the most cited, most influential people in this field. As regards the conference, this conference in a way reminds me of the ECO conference, the European Knowledge Engineering and Management Conference 10 years ago. So the KESW is a conference that tries to gather the community of knowledge engineering and semantic web developers mainly in the eastern part of Europe. So this conference 10 years ago was a first conference of this kind that moved for this edition from Western Europe to the eastern part of Europe, and I'm still quite indebted to Steffen for volunteering to chair this conference. I think some people who are here were already at this conference 10 years ago. The last thing I would mention, or my impression when looking at this Steffen's talk, I noticed these three different terms: semantics, data, and programming. And I think it's something very, very typical, very important. You probably know, or some of you may remember that when semantic web started 15 years ago, it was mainly about the very sophisticated, non-standard programming or procedure approaches applied on very tiny data in AI style. Then something like 2008, there was this link data movement where people started to talk quite a lot about large interconnected data. But only in the last few years, I can see in this community a strong move towards enabling semantic web to a large crowd of developers of software applications, web applications, and so on. I remember that this is something Steffen advocated from the very beginning, that we need to work with large data on the semantic web, but also to bring a huge crowd of programmers into the game. So I think even from this point of view, he's a very special speaker, and I'm very looking forward to this talk.
Thank you very much, Wojciech. I think I'm probably connected. Thank you very much for this extremely kind introduction. I'm too much flattered actually now. And it's a great pleasure to be back here in Prague after this event 10 years ago, though that was not the only time I've been here. So everyone's talking about big data. I do so too. And the first question, of course, when we talk about big data is what is meant with it. And here I just put some typical examples up on this slide. Where does big data arise? For example, with genome data. So we can have, let's say, about 200 gigabytes per person to represent your genome. And video data, we have now some 300 hours uploaded to YouTube every minute. Or we have sensor data. We have worked a couple of years ago with the Xmedia project with Rolls-Royce. This is one of their jet engines, and the very new versions of such jet engines, they produce about a terabit per second sensor recordings to supervise the engines in their flight. And so these newest jet engines, they have about 5,000 sensors, roughly speaking, to make sure that they are in perfect health and you fly safely and land safely and so on. So that's definitely all big data when you, let's say, multiply this with a lot of people and you multiply this with a lot of days or minutes actually. And there are always new devices even to store such large amounts of data. For example, I'm also affiliated with the University of Southampton, and they have produced this disk, which is like this small, it's an optical storage device and can store 360 terabytes in a small disk. I mean, it's still experimental status, but it shows you we can actually, at least in the future, store a lot of data on even small devices. And we have a lot of data, and we produce ever more data. Now, of course, I'm from the knowledge engineering community, and I ask the question for myself or you, how complex is that data? Well, let's just look at two of these examples. When we look at the genomic data, and we can produce these genomic data in triples. I've talked to people from the European Molecular Biology Lab in Cambridge, and they are, some of them at least, are really favorite users of semantic web. And they produce actually large amounts of triples. They say they can produce trillions of triples. But these trillions of triples would correspond to 18 different concepts only. So actually it's not a very interesting triple database, because it doesn't use the capabilities that we have with semantic web data, with linked data, with conceptual data. I mean, obviously there are a lot of challenges that are very highly interesting with exploring the genome, but it has not so much to do with the knowledge engineering part. And a bit similarly with the Rolls-Royce jet engines that we had in this project that produced a bit less than the terabits that new engines have. But basically what you have are noise amplitudes. And obviously you want to really look at whether what they produce is still sound noise, so to say. But it's mostly amplitudes. It's not a very complex format. There are all kinds of issues that you have in filtering such big data, compressing such big data, finding interesting patterns in big data. But the way of storing it in a particular complex format, as we typically like to address in the semantic web, that's not really happening with this big data. So in that sense, they are not complex. But we can look at what the world of big data looks like in terms of variety. We can do so with regard to data models. We have all kinds of data models. Graph data models, relational data, XML, CSV files, MPEG files for videos or for audios. We have specific medical formats like DICOM, let's say for volumetric X-rays. Or we have, of course, PDF or Excel, where a lot of practical data sets are held for e-government data, for example. Nevertheless, there's a large list, and the list is much longer than here on the slides. We would probably talk about dozens or hundreds of these formats that would cover 80–90% of what's around in the world. On the other side, for many of these formats like XML or RDF, you have conceptual models too. Of course, you have a lot of XML applications where the XML data format is used with a particular schema in mind, or maybe where the schema is even formally defined using, for example, XML schema. And we know many of these ontologies sometimes. Let's say FOF would be one of the favorite ontologies with RDFS. Dublin Core came out of the library community, but is also now in RDFS. For example, Mark 81 is a library format, came out, I think, first with XML. Unifact is a very old standardization for CSV files by the United Nations for doing e-business. Basically, you could say there are so many of these formats out there that you cannot really count them in the dozens or hundreds. You have to consider them as being, well, infinitely many. Of course, not in reality. There's less than one format per person, I would say, but there are so many that doesn't really make sense to think of them as a closed list, but rather as an ever-expanding list, where you never get to an end, really. So if we have infinitely many of these different conceptual models, how big are these conceptual models? Let's look back a few years, let's say something like 15 years. And the main SAP system, which talks about people in organizations and what kind of goods are ordered and produced there, how many concepts are typically in such a kind of a system? And I talk here about concepts, well knowing that many of these concepts are realized in form of logical tables, relational tables, or some corresponding business objects and the like. So I summarize all of these different kind of structures into the term concepts here. Experts have estimated that in a system like SAP, there are about 10 to 20,000 concepts that reflect what's happening in the company. So it's a big system, it's a big consulting business still, and we talk about the order of 10,000, 20,000 concepts. Some of the medical information systems I encountered at that time was a system for managing information about transplant patients. And they had to deal with 10,000 concepts, which was a lot for a medical information system at that time. And 10,000 there are not so many transplant patients around. More than a dozen, clearly, but not hundreds of thousands. But the problem is that transplant patients incur almost all kinds of problems during a long period in which they have to take immunosuppressive medication. So there are a lot of different concepts that play a role with their particular disposition. Again, we have in the order of maybe 10,000 concepts, or we had, because what do we have now? Well, we have applications like Wikidata. So we have about more than 1 million concepts in this crowdsourced data collection, which feeds from DBpedia, which feeds from data that people type in, which feeds from databases that are put into the Wikidata data repository. The Wikidata is what Wikipedia is for text. Wikidata is a fact collection to be used by Wikipedians, but also to be used by other people. So you can ask Wikidata, how many people live in Prague? And you will find various kind of answers in different language editions. And the idea is to make this fact-based and make it easier to sync, for example, different language editions. We can again look to medical systems. The National Institute of Health of the US has produced a unified medical language system. Again, we talk about 1 million concepts. I tried to look it up yesterday night, but I couldn't get my hands deep enough because it's kind of a federation of different systems. So you really have to look into a whole set of systems to find out about how many concepts, but it's in the order of 1 million concepts. When we talk about bioinformatics, already almost 10 years ago, there was a journal article talking about 1,000 public databases in the area of bioinformatics. Obviously, these 1,000 databases don't share a common schema, a common logical schema. Again, we talk about dozens or hundreds of concepts being reflected in each of these databases. So we easily end up with several hundreds of thousands of concepts in these public databases. There are more databases at Roche or at Boehringer or at Novartis, or you name the pharmaceutical company. We have the eGov datasets. Fraunhofer in Berlin now has about 200,000 datasets collected about e-government. Some of them are small, just an Excel file. Others are much larger, have statistics data in them. You can guess that not all of these 200,000 datasets talk only about 10 concepts, and that not all of them overlap completely. So we talk about many concepts. I could not count now how many. We have knowledge graphs at Google, Microsoft, Samsung, HP, probably more. Not all of them are very publicly visible. We see a bit of the Google knowledge graph, for example, but there are more companies that now build Google knowledge graphs within their companies. We have new kind of application scenarios. We have sensors. Sensors give us a huge amount of different kind of concepts. Why? Yesterday evening I counted in Wikipedia there's a list of 330 sensor types. But these sensor types, each of them are a class of their own. They go from, air pressure up to moisture measurement and so on and so forth. But each of them is a whole class. For each of them, you can, let's say for temperature readings, you can buy temperature sensors with different specifications for measuring let's say the temperature, whether you have a flu, or the temperature here in the room, or the temperature that a high-end oven produces. So all of them have different specification and represent eventually a different concept. You cannot just replace the one by the other. So again, for these 330 broad types, for each type you have dozens, hundreds, or thousands of different concepts behind them, leading to different type of data. So we have now millions of concepts, not anymore 10,000 or 20,000 that the SAP experts have to deal with. And even when they have to deal with, I once had a master thesis student at SAP, and he was supposed to implement a very simple function. It took him several days to find the 3 right columns to combine. So now we talk not about 10 or 20,000 concepts, but about 1 million concepts. Some of them better organized, some of them worse organized. So Wikidata is still rather nicely organized, I would say. Others are worse organized, like if you have very many sensors from different domains. So how to even find data? And that's what this talk is about. When you have so many different concepts, and even the SAP system is already too complex to program with and implement what you want to achieve, how do you ever write programs with these kind of systems that have such broad data? Broad because it covers data about so many different concepts. To compare this again, we want to program something with genomics data, which is complex to do and requires the expert and everything, but we only have to deal with these 80 concepts. Right? We say we do a kind of a select. Obviously, we run over sequences. We try to find sequences, patterns in the letter sequences of the 4 different letters that we have in the genome. And I'm sure there are other kind of things that people do that are very clever and difficult to understand and challenging. But from a conceptual point of view, it's just like a few concepts at the beginning. And obviously, when we do a Sparkle query, we can still rather easily ask for what are the instances of a particular letter or the particular structure, a base pair, or the like. Now, when we run into Wikidata, and there are some nice interfaces that you can check out, it actually becomes already quite an issue just to find the right concept you're searching for, and the interfaces are nice, and Wikidata is one of the good examples. And then the question is, what would it mean to use a particular concept with a particular numbering like 151735? And can you remember all of them when you program? Because each of the concepts have actually identifiers because they are ambiguous, right? They are the bank that you sit on, they're the bank which are the finance institutes. Both of them have different identifiers in the Wikidata system, but obviously similar labels. And moreover, I mean, these 18 concepts are rather stable, but yesterday I found out I made a mistake here because I pulled this number a half year ago when I gave a presentation in class for my Semantic Web class, and yesterday I checked the number, there are 20,000 more concepts in there over the last 6 months. So it's a moving target. We now have data systems that, as we talk about them, we could divide, let's say, 20,000 by the 200 days that have passed since I did the last snapshot. And so there's like every day 100 new concepts in Wikidata. And so how do we make sure that we still have programmed the system in a way that we deal with this rate of innovation? So how do we approach big data? Now, the traditional way of approaching big data would be, we started with the traditional information architecture. The characteristics are, processes are known, the data structures are known. A lot of the meaning of the data is actually in the code. There is something in the schema too, but a lot of meaning of data in a traditional, let's say SAP-like system is actually in the code. And you find that because when you just look at the schema, you don't understand very much actually. Today's information systems, of course, don't look like the traditional, conventional one that you have in a textbook for databases, but it looks more like a big mess like this, only many more items in there, more different databases in there like this, and more control structures like these here, and more views like these here, and more users, of course, too. And the characteristics is that it's a rather little structure or semi-structured data, and the way to handle that is really not that you could ever have one program that everyone understands. So you really have to make sure that the meaning of the data is really within the data, that you really have nice conceptualizations that are understandable. And when you have different data models, of course you have relational data, you have XML, you have Excel, you have maybe some array database or graph database. My assumption here is we do a kind of graph data model as a common denominator. My guess is that Axel yesterday talked in his talk about enterprise linked data a bit in this direction. Shaking heads, no, maybe not. So I think that's just the simplification that I do here. You need a common data model, whatever the common data model is that you choose. Otherwise, you cannot program with one view against things. And if I just give you a tiny example to make clear what I talk about, you could have, for example, data. I always use musicians, easy enough to understand. So you could have a musician being related to someone else, like this actor, actress Sarandon, and was born on some day. The second is you have all these conceptual models, the schemata, the ontologies, the ways that CSV files are used, and I summarize them as I did when I talked about concepts and use ontologies as common denominator. So Bowie might have a type of music artist and Sarandon being an actress, and so on. And again, also, of course, the important part about the semantic web is that these ontologies are actually live in the same information space, so you can access them. And that's very different than the traditional system design, where you maybe build an entity relationship model, and it's on a sheet of paper or maybe in some design tool, but then it sort of disappears when the system is alive and running. While here the assumption is that you have this data space, you also need to keep the concepts alive and running and accessible in a way that is understandable to the human. I mean, you can of course look at the logical schemata in the metadata tables of your relational database, but that's not highly understandable, not very intuitive to use, and not used a lot, I would say, by many information systems. And then the third point is you have system boundaries. You have a lot of these problems of the broad data because you integrate a lot of data from different places. And of course, the semantic web solution for that is that you use IRIs in order to point to different places. So instead of just saying there is David Bowie, there is a certain unique identifier that allows you to point to a particular person. It's basically just a long name, Java package names. It's work almost the same, you could say. A bit differently, because usually you would expect that if you use such a prefix, you could look up what that entity means in this data space. That's just the linked data recipe that I think makes a lot of sense, even for such an enterprise landscape. Okay, so what do we have now? We have first the observation. We have a lot of broad data. Then here we have this observation that it also applies to the enterprise, and where we sort of like I advertise here a solution without going into much depth as using linked data formats to provide a common data access layer and data management layer to such an enterprise environment or to another information space environment. What I want to start off first for doing programming is a bit of a practical perspective, and I want to explain a practical system we have developed. And as a kind of Drosophila for that, we use the Linked Open Data Cloud. The Linked Open Data Cloud is just a collection of different data sources. Each bubble here is a data source containing triples. And in order to be registered in this cloud by people who make always these nice pictures, you have to cross-link your data source with some of the other bubbles, with some of the other data sources. And not just at the level of the data source as a whole, but at the level of entities within the data source. So for example, somewhere here there should be geonames. I can hardly read it. When it has expanded, each individual bubble became smaller and smaller on this visualization only, of course. And for example, somewhere here is the geonames explaining places like Prague. And there's an entity for that in the geonames information space. But then on DBpedia, which is a kind of fact database for Wikipedia, there is also an entity representation for Prague. And many of these entity representations for major cities like Prague, they are connected. So then there is a cross-link between these two different bubbles. Again, when we talk here in the LOD cloud, Linked Open Data Cloud, we talk about several billions of entities. So I think it was like 10 billions most recently. And again, many, many concepts, thousands of concepts is here actually an under-exaggeration. So how do we program with such linked data? There are several problems that we encounter, that we have to deal with. We somehow need to interact when we hear the programmer with all this linked data cloud. We need to first find particular pieces of data that we want to, and then we need to act with them. Let's say we want to produce some nice labeling of records from some music that we like. And there are many approaches for example, doing semantic data retrieval, which are very interesting, we can talk about. I jump over them. I go more a bit into the task of the programmer who has to deal with such an information bubble. And that's supposed to be now one particular data source. And the task of the programmer is first to understand actually what's in this data source. In the traditional sense, you would assume that you know what's in the data source, and then you start programming. In the SAP system, if you don't know how the database is structured, you cannot really do the programming. Maybe you can use business objects as abstractions, but you cannot just go ahead and do the programming right away. Here, in a way, you should be able to do that, because the idea of the linked open data cloud is that it grows continuously, and there's always a new data source that might come and that you want to deal with. I gave another talk last year for human-computer interaction people, and I said the semantic web is about dealing with the unknown. It's the unknown that you encounter because new data and new concepts come along. Typically, the program would also have to program some code types. So let's say if you want to print out some labels for musicians, you typically would produce some classes. Let's say if you program object-orientedly, some classes for musicians, some classes for labels, some classes for handling all this print-out procedure. And then you would program your queries. So you map from the data bubble into your program code types. There are some, of course, I will mention also later, some mapping approaches, Hibernate, summer, winter, RDF-specific ones, active RDF. But usually what you do have to manually sort of establish a kind of mapping. Sometimes it's sort of like suggests you some names. And then you have to implement the procedures for creating, manipulating, or persisting objects for this data space. Now, we thought about this procedure and that we need to sort of like rethink this procedure. As we have a new way of encountering data, we encounter unknown data, we encounter unknown objects, we have to rethink how to do this kind of programming. So the idea was, let's try to sort of like combine the exploration and the understanding and the programming and make sure to help the programmer all the while. So when we start with some store, we can explore this store using our language NPQL, and then, for example, just be offered concepts and relations. So what we do here is we start at a particular class, general class, like the agent class, fourth agent, and then what this programming system gives you, it looks into the concept space to ask what are the relations relevant here. Relations relevant here are, for example, that a fourth agent may belong to a group or an organization or maybe a arranger or a composer and so on and so forth. So we look here for specializations and relations of this particular class. Just back here. So here, for example, we could pick, we are not interested in agents in general, but we are interested in music artists. And we can do the same for relations. When we have music artists, we can look, what do we know about music artists? There may be an account, there may be an age, there may be a birthday, and so on and so forth. The point being that usually what you do is when you put together this kind of data access, you have to sort of like copy-paste it. But here the idea is you really explore as you go and build your language or build your program as you go. So the node path query language that we do allows us to explore the classes, the relations, and also query for the instances, because you might ask directly, give me all the artists which are in the store, which are music artists, and I want the extension of all that. That's now a very simple query, of course. But once we have that, the good point is that we are in a semantic data space, and we do not only know that there are certain kind of people that are instantiations here, but we have a kind of type to all the extension we get back. And the type is that of music artist, or when we are here, it's rather the set of a music artist. So rather than just saying we now receive back a set of strings, that's the usual thing when you connect to, let's say, a SQL data store. You ask a query, it's typically very often a syntactic query, it's just a string, sometimes a prepared statement, and you put it into the database interprets it, gives you back a set of strings. Which is a bit funny, because we invested all that work of building millions of concepts with even more entities. Then we talk about these concepts, and then we throw away all the type information about these concepts. So the idea was that when we have explored and we found the concept that we're interested in, and we ask that concept, give me everything you have, then what we get back should be typed with the concept itself. Or when we get a set of this thing, then it's a set of music artists instead of an individual one. So the point here is that we don't need a single definition or declaration, because we can just ask the concept space to give us all this information. Someone has engineered the ontology. Why don't we use it? And when we do this, we have one language to do all this exploration and so on, and then development. And then we get for free typing. All artists is a set of music artists. That's the same type used here. When we iterate over the set of all music artists, this is a music artist. So in our programming framework, we know that here we have a music artist, although that's has not been declared, and we can even interactively offer the programmer the suggestion to use this fourth name relationship when programming. So what we have here is then a way to program with this system of unknown concepts and translate everything that we do here into Sparkle queries at development time, and do some type inference as well as at compile time, because we know about the type of this thing. And we query again at runtime when this program runs, because then we want to have the music artist known at the runtime of the system. Similarly, what we can also do then is we can create a new type if we want that, just by declaring that's the same kind of type that we have already here. So with extension we get all the instances of music artist. With intention we get all the intentional description, the properties of the music artist. So we use that to build our programming language type. And when we then create a new artist, well, this is automatically persisted in the back end if that back end gives us the Sparkle update possibility to do so. And then we can go into formalities of what the language is. Basically, the idea of the language is that there are some queries to navigate through this concept and entity space, that there are some possibilities to evaluate queries, to get instances, for example. And there are some queries to get intentions, to get the descriptions of concepts. And then, of course, when you have an algebra, you can do all kind of nice optimizations, like shortening the paths and doing simplifications and the like. And we have also implemented that in LightQ, which is this NPQL language, as an in Visual Studio for the language F#, and use that for auto-completion using such a suggestion system in Visual Studio, using all the automatic typing of extensional queries with the intentional query results. That's a very practical system about exploring things and using this concept information. It's still a bit ad hoc, and the question that seems to work well in practice, but does it work in theory? And that's a good question, because if we don't have a sound theory behind that, it's not quite clear what we really do. What does it really mean that we write a line like that? I mean, of course, we can copy just types, but how will they react when all this underneath changes? What are the implications for the programming framework? What are the implications for the reasoning framework? We need a sound theoretic basis in order to make sure we don't introduce undesired or unwanted behavior. Or even if some behavior is unwanted, at least we want to understand why it's appearing and have a sound grip of why it's appearing. So, how do we do that? Our idea here was to combine the programming language side with the ontology side. Well, and as a programming language, we chose the simplest thing we could imagine. So that's lambda calculus. And on the Semantic website, we chose what is sort of like the canonical standard, which is description logics for OWL, and combined the two. And let me explain why we did and how we did it. The idea is to have static type checking, but to have static type checking for such a space where we have many of these concepts. And these many concepts give us problems, and the programming language side gives us problems. What are these problems? In LightQ, for example, in order to do the static type checking, the queries we want to do must receive types. But the number of types in our system is, quotation marks, infinitely large. As 1 million or more, it's changing by 100 concepts every day. So it's a moving target. So having a static mapping is not really a good solution to build a lasting system. And of course, existing type systems expect complete knowledge. So when we built LightQ, we had the problem that at some point it crashed. I think it was with 1,028 concepts or something like that. Some magic number, right? The whole Visual Studio system just expected that we have something like 1,000 concepts or types to actually pre-compile and do auto-suggestions. So we cannot just arbitrarily work with such kind of systems. When we look at related work, what are the two main approaches? One main approach is to have generic types. I think that's done in semantic web mostly right now. People ask a Sparkle query, and they get back nodes and edges, and they treat them as nodes and edges. That's all nice until you want to have some type checking, because you don't quite know what these nodes and edges are. So when you have some nodes, let's say some literals, and you add them up, is this meaningful? Is it meaningful to do an average? It might depend. It depends on the type, really, right? Of course, you can program all these types, but then you do this, what we don't want to do, that you have to do too much work by hand to deal with all these million concepts. So everything being a node, everything being an edge is very general, but everything you do, you have to ensure you do the right thing all the time. It's a bit like balancing on a line, on a slack line, 100 meters above ground, and you hope you don't fall. Some people can do that, I can't. So, and I had also like a quite of negative experience with building complex knowledge systems without a safety net below such a slack line. We were once competing for who builds the best kind of knowledge system. It was a Halo competition, there were 3 teams, and we only made the 2nd place. And why? Because we had a type safety issue in our system. Our knowledge system, our rules, were not checked for correct typing, and that cost us 10 percentage points of performance correctness. And it was a very simple mistake. Once we found it and added a little bit of typing information, we could easily find this kind of problem and undo it, and we would have won the competition. But 10% out of 100% score is quite a lot of performance that you increase by just finding one single type error. There are the mapping approaches. They partially address this problem because they sort of like take all concepts, that's what they mostly do, and translate them from the concept space, the ontology, into the programming language space. Sometimes also the other way around. The other way around often is less useful because typically you have legacy data that you want to carry in this direction. So we've been there, we've done that. It's nice and good, but it's not sufficient for the challenges that we have with broad data. So what are the examples and issues we have now with mapping and with embedding our complex ontology space into our programming landscape? Well, here's a small example. Here we say that someone who has recorded a song must be a subclass of music artists. So everyone who has recorded a song is a music artist, whether a good one or not, that we don't say. The Beatles are music artists. Machine Gun is a song. Hendrix recorded Machine Gun, and Hendrix was influenced by the Beatles. So a little bit of schema, actually influenced by, has no schema information. That's also very typical for linked data. Half of the triples in linked data don't have any schema information at all. And what we do, of course, is several things. The first problem is we have a mixture of what is in programming languages called nominal typing. You just explain what your type names are, music artist. And you have structural typing. You just give the structure, like a record structure, which is, here for example, the exists recorded song, which is structural typing. And you have the 2 typing paradigms of programming languages. They don't go together very well, actually. Then, I mentioned already that influenced by is without schema. So how do you type that when you encounter it? Then you have inferences. Hendrix is a music artist. So in the programming language world, you do a little bit of type inference, but that's rather simple, and it's typically not based on the properties. You have a bit duck typing sometimes here and there, but it's not quite as powerful as to infer here that Hendrix is a music artist, because Hendrix had that recorded, and that was a song, and someone who recorded the song is a music artist. So you wouldn't have that in the programming language world. And you have the sheer size of the terminology, because the mapping doesn't work so well for copying 1 million concepts. So the question is handling all of this and typing your queries in order to make sure that what you get out of the concept and information space you can put in to your static typing of your programming language. What would be an example for what we want to reject or accept? Here's a tiny example. What we want to do is we have a small query which just says, give me all the music artists. And then we want to apply, let's say, a map function to do it over the whole list of results. And we just want to select the influence by, whatever, to do some nice printing about it. And the problem is that music artists, according to this conceptualization, are not necessarily influenced by anyone. So it's not guaranteed. Maybe it is, maybe it isn't. So actually, when we apply that, we certainly would also have an empty set or something like that, where we would try to do something with the empty set, and then the system would break down. So actually, this should be rejected by our system. And it is actually rejected because the query is typed by music artist, and that type, music artist, is not a subtype of the influenced by, and that influenced by is given as a type here to this particular function G, which is used for the mapping. So you see, you need also in this 3-line example to do already a little bit of type inferencing and type forwarding, and then checking of whether the two types fit to each other. Another example that should be accepted, when you do a query for all the music artists that were influenced by someone, then suddenly a music artist who is influenced by someone is a subclass of someone who is influenced by someone. Now you could apply your map function. And that, of course, also is an example for a slightly more complex query than the one before. So we want to have static type checking, and the challenge now is to have a programming language that accepts concept expressions as types and can deal with inferences. That's what we suggest for Lambda DL. So what are the core ideas? Well, we use a very simple typed lambda calculus, and it just assumes that first you have atomic types and you have function types. Okay, that means you have an atomic type like string or Boolean, and then you can map from types to types. That's what the function does. And you can have higher level functions, of course. Then we add as further elements concept expressions as types. They correspond, roughly speaking, to our intentional NPQL queries. Yeah, you have asked for music artists, and you have asked for, well, give me also all your properties and so on. Yeah. And we are talking about instances that are typed by the extensional part of the NPQL queries. When I ask for all the music artists, I get the Beatles, and they have the type music artist. And you add knowledge, then you add the knowledge from this information space where you have your ontology and your data, and do all the inferencing there. Now, how do you do this inferencing? I think most of the people here in the room will be knowledge engineering people, so they will know description logics. Maybe there are, who doesn't know description logics, who has not heard about it in this room? There's one person, okay. Then let me do the 1-minute summary. So basically the description logics here is just a fragment of first order predicate logics. And what you do is you have the possibility to describe concepts by putting together concepts with other concepts. You can describe that an influenced musician is a music artist who was influenced by someone. And that's what's done here with several logical connectives. And then you have two kind of axioms. You have terminology axioms, where you basically say one class is more specific than another class, or the same as another class. And you have kind of a database. And in the database you just say, there is an object which is instance of a concept. Beatles is instance of music artist. Or you say two things are related, like Hendrix recorded Machine Gun. That's all. Okay? So a little bit of logics up here, and then you say how two different concepts are related to each other, and here you say what your data is. A very simple table that only has either it's a 1-column table for the instances, or it's a 2-column table because it relates two instances via a particular property with each other. Now, the lambda calculus is a very universal model of computation, and it's a bit abstract, I must agree to say. The idea is that you have basically two kinds of operations, namely you have abstraction and application. Abstraction means that you take a term and then you can put a lambda abstraction in front of it, and that's a bit like taking a term and making a function out of it. And what you can also do is you can do application. That means you have two terms, and that basically means you take something, a value or a function, and put it in another function. So here would be a typical lambda expression, which is quite complex. It takes several parameters. Some of the parameters are higher order parameters. You can put a function into a function and use it. And you have then certain evaluation rules. And lambda calculus is Turing complete. With the evaluation rules, you evaluate with these rules so long until you end up in a particular thing, what is called a value. And the syntax of values is very simple. It's stuff that only starts with a lambda x or a lambda expression and does not have another value here. So basically, it's a kind of production rule thing that evaluates until it can run no longer. And people have been clever and proved that this is the same as programming in BASIC or Java or whatever else. The syntax we use is pretty much core. What we use is not the very simplest lambda calculus, but a typed one. The typed lambda calculus works exactly like the lambda calculus, but in addition, every expression is typed. Every term is typed. And for what we do here for the typing is, we have all the usual types we had before, string, boolean, but in addition we have concept types. That's what's indicated here. And you can put also these concept types to make functions out of them. Now, there is, when you look at typed lambda calculus and our stuff, lambda DL, the good thing is there's not a lot that changes. You look here at the evaluation rules, and there is no change at all. You look at some typing rules, and there is something new. Namely, for example, one thing that we allow here is a nominal description logics type. So we can say here is a type that consists only of one instance. For example, we create a type out of the Beatles. It's a small syntactic trick that we need to do. And we have new kind of rules. Namely, we have all the old rules from typed lambda calculus before, and in addition we have rules for checking that an instance belongs into a class or that a class is a subclass of another class. The important point here is that we don't do this proactively. We only apply these rules for typing when necessary. So we do it in a lazy way. And that's the way how we deal with sort of quotation mark infinitely many types, because we don't need to put 1 million types into our programming language. We let them sit there in the information space, and when we need a type, we take it. And when we need to know something about how two types are related, then we compute that. So it's a lazy approach to handling this size issue. There's more stuff to be said about that. We need now new types for concept sets. We need to explain operators like map. I already gave an example for that. Then there are interesting issues, for example, how to deal with queries. One could handle queries with infinite sets, because in an ontology you can explain that everyone has a father. So my father has a father, and his father had a father, and so on. So if I ask for all the fathers, that would give an infinitely long chain. But most of the chain would be rather boring, because it would talk about only anonymous entities about whom we would know nothing. So right now we handle it in a simplistic way, namely that we only care about instances we know in our database. We have some interesting stuff about the interaction between programming language and the ontology, because, for example, we can decide to do something in the programming code depending on which type someone belongs to. So you could behave differently for artists that have been influenced by someone than for artists not influenced by someone. And there's an interpreter that has been developed in F# and uses the Hermit reasoner to realize the whole concept, this lambda DL calculus. And there are some theoretical results that basically say that when you have some nice typing, then a well-typed closed term does not get stuck during evaluation. And then the programming languages people, and we do the like, say, with some few exceptions, for example, when you handle lists, you could run into an empty list and ask for the head or the tail of that empty list. And that you can never resolve because, well, of course, you cannot solve the halting problem in general. So the typing helps you. It does not guarantee you that what you do is completely correct. If you would do that, then the halting problem would be solved. So lambda calculus here gives us quite some results. There are still many open issues that we look at. For example, to have more powerful queries, conjunctive queries, for example, not just concept expressions as queries. To look at generic programming, which we don't handle very well so far. Because you have so many concepts, you want to provide functions that apply to many. For example, a print function for printing a label of an instance should apply to maybe even all the 1 million concepts that we have in Wikidata. And if there are now, during my talk, 10 concepts more, that function should still be able to work with these new concepts. Then, of course, what we have not considered yet are changes to the knowledge base. If we just have additions to the database or removals from the database, that's not critical. If we have changes to the T-box now, especially if we have deletions from the T-box, we cannot handle that very well so far. So there's still things to be done about changing knowledge bases. About the anonymous entities, we are not fully sure yet. We have found the best solution. And we still have to think about meta-programming. We also want to query for instances, but we also want to query for concepts. And the funny thing there is that even the DL people have only a kind of awkward way of querying for concepts. Because all the instance querying is based on a nice semantic theory. But the querying for concepts is just based on a syntax. And sometimes with a little bit of semantic constraints, but it's primarily a syntax-based thing. And so we have not integrated that in any meaningful way. So, to conclude, what is the presence of broad data? I have argued today that we have grown from in the order of 10,000s of concepts over the last 15 years to the order of 1 million concepts that we need to handle in our information systems. And the whole thing is continuing to grow. We add more sensors, new types, we add more concepts that people provide, we integrate new databases all the while. I think the problem, as I've described it today, has not been recognized as a problem very much. Maybe some people would claim it's not a problem. I think it is. I think not treating it as a problem will lead to brittle systems because conceptual space changes, the data changes, which have high maintenance efforts and only considering the information space as graphs, I think does not really exploit what you might do with these information spaces. And that would be a loss of opportunities. We need new methods to explore and find better what's in these information spaces. We need to find and understand and relate things. So Linda today talked about, for example, doing stories. I could think that when you look at an information space where something is in there and you want to program that, that's also a kind of story that what you want to do with this kind of data. It's not exactly the same kind of story Linda talked about, but it's also a kind of story. You build a system to have a kind of meaningful interaction with the person who uses the system. And that's more than just having a simple query. It's a program that needs to be maintained. And for example, we need to explore more like how can we come up with good maintenance procedures for programs like the ones I suggested today. I thank you for your attention, and I thank the other people who worked with me on stuff I presented today.
Let's have the questions.
Hey. I have a question that is basically about how this relates to the existing techniques of constraint languages for OWL, for example. There are several proposals that allow to create constraints that are evaluated by, for example, distinct conjunctive queries or stuff like this. And it seemed to me quite similar in terms, for example, of generating of these constraints. What's your opinion?
I don't know these constraint languages. I know a bit of constraint programming, but when I looked into that, that was already also like 15 years ago. And from my experience then, I could not quite understand your remark, but maybe you're correct, and I just don't know the field well enough. Maybe you can take this offline, you can explain me a bit more about this kind of constraint languages. I have not seen in the field of constraints that they take typing into concern, really. But maybe I'm mistaken there, but I would love to learn about that. If
okay, so let's leave it maybe for later. I will give a chance.
Maybe I have a slightly related question to what Peter just asked. So the static type checking is quite nice, but some of it can be also achieved by runtime type checking. And I think there are approaches like Shackle, these data shapes constraints that are developed at W3C now, that can deliver the same functionality but in runtime. So
why would you want to delay it to runtime? I mean, when I develop a program and I compile it, or I just deploy it. I mean, maybe you have an interpreter and you don't compile it, but you just deploy it. And I would like to know all the mistakes, or at least as many mistakes as I can get very early. And when you look at the programming languages community, they spend a lot of efforts on doing all kind of fancy things in order to make sure that at the point when they deploy a system, they know most or hopefully all of the mistakes. So I don't see, I mean, why should the user ever encounter a blue screen? Why would the user ever want that?
Well, I think maybe there's a fundamental difficulty with working with linked data or raw data, as you termed it, since you often don't know what kind of data you will encounter. So that's why it might be quite difficult to do static type checking in advance. But
okay, that's a good question. How can we envision to deal really with concepts that we don't know yet? And to some extent it's not possible. Then the question is, of course, how unknown are these new concepts? If these new concepts inherit something, then we maybe inherit also some functionality, right? So let's say if I just add a concept somewhere down in the tree, and that inherits all kind of nice things. Let's say we make a new type of person. I don't know. Let's make it a conference attendant here as a new type. Maybe not best programming practice, but let's do it just for the sake of the argument. And then, of course, we inherit a lot of information about that person as a name and a birth date and so on and so forth. And all the functionality we developed for persons in general, we inherit and can apply even to this unknown concept. And if we now really come up with something else which doesn't fit anywhere, some magical unicorn that's not in our Wikidata ontology, and we don't know anything about it, then we are we cannot do much. Maybe we could ask the user, can you build a program for us? Even then it would be nice to have the type checking, because even at that sort of runtime for the user, what he's doing is kind of building a program, and we can try to tell the user what is a valid program and what is not a valid program.
Yeah, I very much agree. I think that something more generic, like more generic types, can work around these limitations of dynamic data that we don't know yet. Mm-hmm. I think we should definitely strive for something more concrete, more specific than the very generic type that you mentioned for Spark results when we don't know anything about the type of the income. Mm-hmm. So thank you.
Thank you for your question.
Maybe just a little question. You showed some description logics. Would you show us some kind of AL logic, I think? Does the choice of description logic have any, or is the choice of description logic important, or can you just apply?
It's a bit more than EL because we have disjunction. And so basically we end up in more or less the complexity class of ALC, but we also have nominals, so that goes beyond ALC. What I want to have in the end is that, of course, maybe at compile time, we use this rather powerful logic which is restricted. I mean, we cannot do interactive inference yet with this kind of complexity classes, but that we use that at runtime, but then use simpler complexity classes for doing runtime queries, using OBDA and the like. We have not looked deeply enough yet whether to see where the do's or don'ts of this thing are. For the compile time, we definitely need more than EL. For the runtime, it would be nice to stay in that kind of complexity class.
Your choice of F# seems like an Achilles heel to me.
What?
An Achilles heel, prevention to kind of a blocker to adoption.
Well, so for LightQ, the reason was very simple. Microsoft financed that research, though of course F# is quite a nice language and it's actually completely open source. So it's not a Microsoft closed shop thing, but one of the main motivations was that Microsoft funded that part of the research. Now for the lambda DL, it's really, well, just like a smallest thinkable subset. It's nothing to do with F# at this point.
So are all these concepts portable to Java, JavaScript, Python?
These languages are big, so porting these things may have problems in the details that I don't see now, or we as a team don't see now. So it's a bit hard for me to say, oh, there will be no problems. I cannot say that as a science, as a researcher in good conscience. I hope so. I don't see a good reason why there would be a big problem, especially since the approach we have is rather loosely coupled only. Right? We don't have a very tight embedding of our principles of lambda DL into the evaluation of the programming language. So my positive speculation is, yes, it's transportable, but beware of all the details. I don't know it yet.
No more questions? So let's thank again the speaker and the session.
Thank you.